Welcome to WikiPodcast. Think about, the really dynamic stuff in physics. Car crashes, billiard balls flying everywhere, even rockets heading to space. What's the core principle behind how all that motion and interaction works?
Yeah, it's a great question. It's not just about force, is it?
Right. There's something more fundamental about moving things. A property.
Yeah,
Momentum.
exactly. Momentum. And that's what we're diving into today using the material you sent over. We're going to unpack what momentum really is.
Okay.
It's the key, really, to predicting what happens after things interact or collide, a cornerstone of classical physics.
So our mission today, get a grip on momentum
Yeah.
and why keeping track of its conservation is so important.
Let's do it.
All right, so starting basic, what is momentum really?
At its heart, linear momentum is, well, it's pretty straightforward conceptually. It's just an object's mass multiplied by its velocity.
Mass times velocity, like how much stuff is moving times how fast and in what direction.
Precisely. We usually use p for it, so the equation is just p mv.
And you mentioned velocity, which means direction is baked right in.
Absolutely critical point. Velocity is a vector magnitude and direction, so momentum has to be a vector too.
Okay.
The direction is just as vital as the mass and speed. And the standard unit, kilogram meters per second, kgohms.
Kilogram meters per second. Your notes mentioned something interesting. It's equivalent to a Newton second.
Yeah, dimensionally speaking, which is kind of a neat hint about how momentum connects to force.
How so? Force times time.
Exactly. Think about it. If you have, say, a 1 kilogram ball moving north at 5 meters per second, its momentum is 5 kilojoules north.
Okay.
If that ball slows down, speeds up, or turns, its velocity changes, right?
Right.
And if its velocity changes, its momentum changes. And that change only happens if a force acts on it.
Ah, okay. So force is what changes momentum. This sounds like Newton's second law, but maybe a different angle than FMA.
You got it. The source material points out that Newton actually phrased his second law in terms of momentum originally. Yeah. He said the net force on an object equals the rate its momentum changes. So F in charge dpt. The change in momentum over the change in time.
FdP/dt.
Now, if the mass stays constant, dp/dt becomes m times dB/dt, and dB/dt is acceleration.
Which gets us back to FMA.
Exactly. But the FdP/dt form is, you could say, more fundamental. It even works if the mass is changing.
Like a rocket. Burning fuel, losing mass.
Precisely. That formulation handles it perfectly.
That's a really useful way to think about it. Force tells you how momentum is changing over time, and this leads to impulse.
Right. Impulse, usually written as J. Impulse is basically the total change in momentum that happens because a force acted over some time interval.
So not the rate of change, but the total kick.
Yeah, exactly. The total effect. Mathematically, it's the integral of force over time. But look, if the force is constant, it's just fets.
Change in momentum equals force times the time duration.
Simple as that. That fet is the impulse delivered.
Okay, let's use that example from your notes. The 1 kilogram model airplane starts at rest, accelerates to 6 meters north, and this takes 2 seconds.
Right, so initial momentum, mass is 1 kilogram, initial velocity is 0, so initial is 0.
0.
Final momentum. Mass is still 1 kilogram, a final velocity is 6 meters north, so final 1 kilogram, 6 meters north equals 6 kilojoules north.
So the change is just 6 kilojoules north.
Yep, from 0 to 6.
And if that change happened over 2 seconds, what force was needed?
We use F, so that's 6 kilojoules north, 2, which gives us 3 kilojoules north.
Which is 3 newtons north.
Exactly, 3 newtons. And you see how the units work out. The impulse was 6 newton seconds, which equals the momentum change of 6 kilojoules. It all connects.
Okay, that relationship between force, time, and momentum change is clear. But the really big idea here, the one that unlocks so much, is conservation, isn't it?
Absolutely. The law of conservation of momentum. This is huge. It says that if you have a closed system...
Meaning no outside forces interfering.
Exactly. No net external forces acting on the system as a whole. In that case, the total momentum of everything inside that system stays constant. It doesn't change.
Stays constant, even if things inside are, like, crashing into each other or pushing apart.
Even then, the total momentum before the interaction is exactly equal to the total momentum after.
Why? What makes it stay constant?
It actually comes directly from Newton's third law. For every action, there's an equal and opposite reaction.
Okay, how does that connect?
Well, think about two objects colliding inside our closed system. Object A pushes on B with some force.
And B pushes back on A with an equal and opposite force.
Right. Now remember, F equals dp/dt. Force is the rate of change of momentum. So if the forces are equal and opposite, the rates of change of momentum they cause are also equal and opposite.
Oh. So if A's momentum changes by, say, +5 units because of the force from B.
Then B's momentum must change by -5 units because of the equal and opposite force from A.
So the changes cancel each other out when you look at the whole system.
Precisely. The total change in momentum for the system, A plus B, is 0. dp1 plus p2 dt equals 0. If you sum up the individual momenta of all particles in the system, that's total equals yv. That total vector sum does not change over time.
It just gets shuffled around between the parts.
Exactly. Redistributed. Your notes emphasize this works universally in a closed system. Collisions, explosions, gentle pushes, whatever. Total momentum is conserved.
That makes analyzing collisions, like, way more manageable.
It's the key tool. Knowing the momentum before lets you figure out things about the momentum after, especially if you combine it with energy principles. Your sources split collisions based on energy.
Okay, first up, elastic collisions.
Yeah.
The source says kinetic energy is conserved here, too.
Correct. In an elastic collision, both momentum A and D kinetic energy, that's MB1, are conserved.
Are these common in the real world?
They're mostly idealizations, but some things get close, like interactions between atoms or subatomic particles. A spacecraft doing a gravity assist around a planet is basically elastic. And billiard balls.
Cool balls. They seem pretty bouncy.
Yeah, they're often used as a good, almost elastic example. Very little energy is lost to sound or heat, relatively speaking.
Your notes had a really cool simple case. Two identical masses colliding head-on, one starts at rest.
Oh yeah, that one's great. It seems weird, but if ball A hits stationary ball B, and they have the same mass, collision is elastic and head-on, ball A stops dead.
Stops completely.
Stops completely. And ball B takes off with the exact velocity that ball A came in with. They just swap velocities.
Wow. Why does that happen?
It's the only way to satisfy both momentum conservation and kinetic energy conservation simultaneously in that specific setup. The notes mention it looks simpler in the center of mass frame.
Okay. And if the masses aren't equal, like a bowling ball hitting tennis ball?
Then you use both conservation laws, momentum and kinetic energy, to solve for the final velocities. It's a bit more algebra.
But intuitively.
Intuitively, it works like you'd think. The heavy bowling ball's velocity barely changes. The light tennis ball goes flying off with a much larger change in velocity. But the total momentum and the total kinetic energy before and after are the same.
Okay, so elastic means kinetic energy stays the same. What about the other kind?
Inelastic collisions. Here, momentum is still conserved, always in a closed system, but kinetic energy is not.
Where does the kinetic energy go?
It gets transformed into heat, sound, maybe permanently deforming the objects.
It's like a car crash, crumpling metal, loud noises.
Yeah.
That's lost kinetic energy.
Exactly. That's a classic inelastic collision. Or think simpler. A blob of clay hitting a wall and sticking.
Or the notes mentioned a bug hitting a windshield. That's definitely inelastic.
Yes, and those are examples of perfectly inelastic collisions.
Perfectly inelastic. That means they stick together after, right?
That's the defining feature. The two colliding objects become a single combined mass moving with a single final velocity.
That sounds like it might simplify the math.
It does, quite a bit. Since they stick together, the conservation of momentum equation is just total momentum before equals total momentum after. So MAVA1 plus MBV1 equals MA plus MBV2.
The sum of the initial momenta equals the combined mass times the final velocity.
Yep. If you know the initial masses and velocities, you can easily find the final velocity of the wreckage or the clay blob or whatever.
Your material also mentioned something called the coefficient of restitution, CR.
Yes. That's basically a number that tells you how inelastic a collision is. It measures the bounciness, you could say.
How does it work?
A CR of 1 means perfectly elastic. All kinetic energy related to the bounce is conserved. Maximum bounciness.
Like the ideal pool balls.
Right. A CR of 0 means perfectly inelastic. They stick together, 0 bounce, like the bug on the windshield.
And values in between.
Values between 0 and 1 represent most real-world collisions, where there's some bounce, but some energy is lost. For a simple case like dropping a ball, the CR is related to the square root of the bounce height divided by the drop height. It quantifies the energy loss. Makes
sense. And momentum conservation isn't only for things coming together, right? It works for things flying apart, too.
Absolutely. Think about an explosion. You start with, say, a grenade sitting still, 0 total momentum.
Okay.
Then it explodes. Pieces fly everywhere, each with its own momentum. But if you could add up all those momentum vectors, magnitude and direction,
The total sum would still be zero.
Exactly. The positive momentum in one direction is perfectly balanced by negative momentum in other directions. The total vector sum remains zero. It's just distributed differently.
Like a rocket launch.
Perfect example. The rocket expels hot gas downwards at high speed. That gas has downward momentum.
So by conservation.
The rocket must gain an equal amount of momentum upwards. Action, reaction, momentum, conservation, it all ties together.
This principle feels really, really fundamental. Does it just apply to these sorts of simple particle examples, or is it broader?
Oh, much broader. We usually simplify to one dimension, but momentum's a 3D vector. Conservation applies in all 3 dimensions independently in a closed system. And the idea goes way beyond simple solid objects. Your notes touch on this. It applies to systems where mass changes, like rockets, to continuous stuff like fluids or deformable solids, where you talk about momentum density. Even electromagnetic fields carry momentum.
Wow. Light carries momentum.
It does, and the concept is crucial in quantum mechanics and relativity, too. In relativity, it gets combined with energy into something called the four momentum. So yeah, it's incredibly fundamental and far-reaching.
Given how central it is, it's kind of amazing to think about how we even figured this out. What's the history there? Was it obvious?
Not at all. It took a really long time. Early ideas way back involved concepts like impetus, thinkers like John Philoponus, later Ibn Sina. They suggested that when you throw something, you impart some kind of internal motive force, an impetus, that keeps it going for a while.
Sort of like momentum, but maybe thought of as a force within the object.
Kind of. It was a step away from Aristotle, who thought you needed a continuous external push to keep anything moving. Then in the 14th century, John Buridan refined impetus was maybe proportional to weight times speed. Getting closer.
Weight times speed. Almost mass times velocity.
Almost. Then in the 17th century, Descartes talked about a quantity of motion, basically size times speed, and he actually thought this was conserved in the universe.
But you missed the direction part, right?
Critically, he thought if something bounced off a wall with the same speed, its quantity of motion was unchanged. But changing direction is a change in velocity, therefore a change in momentum.
No.
The vector nature is absolutely key.
So who fixed that?
Figures like Christian Huygens, John Wallace, they worked out more correct rules for collisions implicitly using the vector idea.
And then Newton.
And then Newton, in his Principia Mathematica, really formalized it. He defined quantity of motion explicitly as mass times velocity, the vector quantity we call momentum.
Did he state the conservation law?
Not as a separate law, no. But it follows directly from his third law, the action-reaction principle we discussed. By the early 1700s, the idea of momentum and its conservation was pretty well established in physics. It was a long evolution.
So, bringing it back to today, why should you, listening now, really care about momentum and its conservation? What's the takeaway?
Well, because this one idea, conservation of momentum, is just an incredibly powerful predictive tool. It lets us understand and analyze so many interactions.
Like what?
Like everything from designing safer cars, understanding impulse and momentum changes in crashes, to calculating rocket trajectories, or figuring out how to design sports gear for better impact, or even analyzing particle collisions in giant accelerators.
It's practical and fundamental.
Absolutely. It gives you a way to look at a complex interaction, maybe one where the forces are messy and hard to track, and still say something definite about the outcome. You just look at the total momentum before.
And you know it has to be the same after, for the whole system.
Exactly. It's like a fundamental accounting principle for motion. The universe insists that the total momentum is conserved in any closed interaction.
It really does feel like one of the universe's core rules.
It seems to be.
Okay, so let's recap. Momentum. It's mass times velocity, PMB/AV. It's a vector.
Crucially, a vector.
Force is the rate of change of momentum, FdP/dt.
Right.
Impulse is the total change,
Right.
fate.
Yeah.
And the big one, in a closed system, the total momentum never changes. It's conserved. This comes from Newton's third law.
Perfect summary.
And this conservation lets us understand collisions, elastic ones where kinetic energy is also conserved, and inelastic ones where it isn't, like things sticking together,
Yeah.
and separations like explosions or rockets.
Exactly. It covers the whole range of interactions. And thinking about that conservation, it's interesting, isn't it? Energy can change forms, kinetic potential, heat, sound.
Right.
But momentum in a closed system seems to just transfer. It doesn't convert into potential momentum or heat momentum. It just moves from one object to another.
Never created, never destroyed within the system, just passed along.
Yeah, that persistence, that simple transfer. What does that really tell us about how space and motion work? It's something fundamental.
Definitely something to chew on. What does that unwavering conservation imply about the fabric of reality itself?
Thanks for listening. Write us your opinion in the comments on why is the conservation of momentum such a powerful tool for predicting the outcomes of collisions. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.